Hi everyone, and welcome back to this series of Electrical B7 Power System Engineering PO exam. This is the second part of the question I previously solved it. This part is mainly theoretical part. It has two parts. Okay, let's go and solve each one. So here it says, draw a physical diagram of a single phase step-up transformer 1 to 2 ratio, including windings and the magnetic path, identify the flux path, and show polarity dot notation for the winding. So here, this is the physical diagram of a transformer. So basically, this is a single phase transformer. So we have here the core. And then it is 1 to 2 ratio. So basically here, if I use, let's say, 3 turns here, so this would be 6 turn here, just to show that you have this correct. Okay, now here is the direction of the current coming from the source. This is the direction current of the current going to the load. It shows here, show the magnetic path. So now using the right hand rule, when the current is going in that direction, this would be the direction of the flux. Let me use a different color here. Okay, so basically here, this would be the flux will be coming in this direction. Okay, going this way, and coming this way. So this is the flux direction. But now here, the flux will be going this way. There will be some leakage flux here. So there will be some leakage flux in this side, and also in this side as well. So there will be some leakage fluxes here as well. And again, from both sides, there will be some leakage flux here and there as well. So this is the leakage flux. Then it says here, identify, show the polarity dot. Now the polarity dot, when the current enter, so if this is the dot here, this is the dot. Let me have some, again, different color again to show that clearly. So let me have this black. So this is the dot in the primary. So when the current enter at the dot, the current will leave at the dot from the other side. So here will be the dot here. So the current in the primary enter the dot, the current in the secondary leaves the dot. And this is always the direction of the current in the transformer. In the primary, the current is enter because it's coming from the source. Here is your source. And from the secondary, it will be basically going to the load. So this is always the case, the dot notation of the transformer. Let's go for the second question. It says here, draw a phasor diagram of a single phase transformer step up 1 to 1.5. So the ratio here of the transformer is equal to 1 over 1.5. I will leave it as such. The transformer full load is 0.8 lagging. Okay, so the power factor is equal to 0.8. And from this, that your theta will be cosine inverse of 0.8, which is equal to 36.887. Include primary and secondary voltage phasors, primary and second current phasors, magnetizing and core loss current phasors in your diagram. Identify the important angles. So here, to draw the phasor diagram, we need to have a model, and the model that we'll be using is basically the approximate model. This is always the case that we have it. Now you have the right to use refer to the primary or to the secondary because it's not specified. So I will use refer to the primary. So this will be your VP, this is your IP, this is your AVS, and this is your IS over A. Now this is your R equivalent and JX equivalent of your winding. This is your RC and this is your XM. So we will have here IC and here we'll have IM. So we'll have IB, IC, IM, and IS over A. This is the primary current, the secondary current. This is the current represent the core loss, okay, which is this one. And IM representing the magnetizing part of the current. So these are all the phasors here. Let's see how to draw the phasor. We always start with AVS as our basically is as our reference vector. So this is 1 over 1.5. This is your A, and this is your VS. So we start here with a vector with a 0 angle. So this is always assumed a 0 angle. So this is your VS divided by 1.5. Okay, now if you apply KVL here, you will see that your VP is equal to your VS over 1.5, which is the AAVS, okay, angle of 0 plus IS over A times R equivalent plus JX equivalent. Now, IS will have the minus theta, which is basically the power factor angle. So the current, the angle here, so we will have here your IS over A, and the angle is 36.87. Actually, it's minus. Okay, so because this vector angle 0, this vector has an angle of minus 36.87. Now, to complete the KVL, IS over A, which is this, multiplied by R equivalent, which is this one. Now, R equivalent is just a scalar. Now, I will move this vector to the tip of this vector, multiply it with IS. So this vector will be IS over A times your R equivalent. And this vector is parallel to this vector, okay, because R will not change the angle. Then we will have IS over A times JX equivalent. This would be a vector 90 degree with, so this is your JX equivalent times IS over A. Now, why it's 90 degree? Because of the J. J is nothing but 90 degree. Now, let me just change the color to make things a bit clearer here. Now, adding VS over AVS with an angle 0 plus R equivalent IS over A plus JX equivalent IS over A. These are the three vectors. When you add them, then we will get your VP using the KVL. And this angle is basically your angle delta. This is called the power angle or the torque angle. This is the power factor angle. Okay, now still says here find the core loss current, which is IC. Now IC and VP, they are basically in phase. Okay, why in phase? Because RC doesn't change the angle. So your let me again change the color here to have something different. So basically here you will have here your vector, which is your IC. It is in phase with VB because basically your VB is RC times RC, IC times RC. So basically they will be in phase. Now this is JXM. Okay, so there will be a 90 degree between the VB. So the current IM will equal to VP, angle of delta, divided by JXM, or this will be VB angle of delta minus 90. Okay, so here you will have, it will be 90 degree, so there will be a minus 90 here. This is your IM. And this will be a 90 degree. This is a 90 degree. And the angle from this would be basically your the angle of delta minus 90. Okay, so that is the phasor diagram. The most two important angle is the power angle and the power factor angle, and this is the total phasor diagram of a transformer.